every value of the index, every value of I determines a term. Okay, so now let's say when I value is 0, and then we compute r to the power of I. I specified r is not equal to 1. So how about I give you another restriction? Okay, I also want to specify r is not equal to 0. So we can talk about r to the power of 0. I can use 1. Okay. Again, each value of the index will determine a particular term. I value of 1 will give you r to the power of I value of 0. I value of 0 will give you r to the power of 0. That's the initial term. Initial term is r to the power of 0, so it is 1, right? And then the next term is determined by r value of 1, so you have r, right? And then the term after that is determined by r value of 2, and so on. Okay, so you have r squared. I wanted you to write down the first 4 terms. Okay, the term after that would be r cubed. My meaning in here is, so do not stop here. The given series is not the same thing as that. Okay, we're trying to define the sum of infinitely many of terms. Okay, you have to write dot dot dot, or otherwise the meaning is different. Okay, at this point you'll see you can recall the meaning of a series. I think you can treat the series I mentioned the last time. You can treat the series as an operation. We are trying to define the meaning of adding many terms. It's comparable to this. So now let's say 1 plus 2 equals 3, right? The 3 is called the sum. Now the plus sign is the operation. Now for the series, we are trying to define the operation. We are trying to define the meaning of adding many terms, adding infinitely many terms. Okay. You can also treat the thing as a symbolic notation. So that's a series. So rather than question 8. The important thing for a series is to define the sum. What we mean by adding infinitely many of terms, right? To define the sum, now let's recall what we did the last time. We are going to use partial sum sequence. Okay. Each value of I will determine a partial sum. Now let's say i's value of 0 is nothing but 1. Initial term. Again, I have a convention to call the first term 0. You look at the mouse cursor. That's term 0. That's my term 1. That's my term 2. I just want the notation to be consistent with the index. Okay. And likewise, you do not know the value of r. I think for S1, it means the sum of term 0 and term 1. So you just write the answer something like this: 1 plus r, right? And then S2 is the sum of term 0, term 1, and term 2. Okay. S2 is 1 plus r, and then plus r squared. At this point, I want you to know S1, S2, actually for any n, Sn is well defined. By that we mean you know how to add finitely many of terms. We are going to use the sum of finitely many of terms to define the sum of infinitely many of terms using the tool of limit. I told you the tool to handle infinity is to use limit, right? Okay, I'm going to move on to C. Okay. In C, now we are going to find any partial sum for any value of n. Okay. I did not know how to write the question properly, but you see the meaning. Sn, it means the sum of the first n plus 1 terms, starting from term 0 to term n. If you use the dot 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 notation, it means 1 plus r, right? And then plus up to r to the power of n is the sum of the first n plus 1 terms, term 0, term 1, up to term n, right? if you are trying to use the summation notation, so this one, it means the you just use one of the two notations. The same thing. You could write I starting from 0 up to term n. You write all the terms. So now let's say r to the power of I. Okay. You can use one of the two notations. Okay. In this question, again, Sn is well defined, so because it's possible for anybody to compute the sum of finitely many of terms, to compute the sum of n terms. Okay. So this one, we have seen a formula before, right? We have seen a formula before. You recall what we did last time? Adding 1 plus r up to r to the power of n, you have a nice closed form. So this one is 1 minus r. It's a quotient. The whole thing is a quotient. On denominator, you have 1 minus r. On numerator, you have 1 minus r to the power of n plus 1. I told you why last time, even, right? Okay. That's my intention on question C. Again, so because the geometric series, we call this one the geometric series. Okay. It's so important. I really want you to reproduce the solution for the assignment, on the assignment. Okay. This formula is true when r is not equal to 0, when r is not equal to 1. To finalize the assignment, I'm going to include the restriction r is not equal to 0. So because 0 to the power of 0 is kind of undefined, right? I'm trying to avoid that. So you have the answer to question C. The answer to question D is kind of how we define the sum of infinitely many of terms. What do we mean by the sum of the series? You see the series, if you look at A, the series you are trying to add infinitely many of numbers. R is a real number. Okay. So what's the meaning of that? Again, the definition is actually the definition of the sum of adding, the definition of adding infinitely many of terms. We are going to use the partial sum. We are going to take the limit of the partial sum as n approaches infinity. We are going to use that to define the sum of the series. Okay. So that's kind of the new way. Okay. I think I have a better way to show you the meaning. Okay. Now, in this question, we are trying to define the sum of the geometric series, I starting from 0 to infinity. It means 1 plus r squared plus r cubed, and adding forever. Okay, you remember the pizza question? Half pizza and then adding 1/4 of pizza and adding 1/8 of pizza. We are trying to define the meaning of that. Okay. So this one, the series is r to the power of I. Again, we call this one a geometric series. The reason is, so there's a common ratio. Okay. I told you last time, r divided by 1 is r, right? R squared divided by r is equal to r. So basically, the ratio between every pair of consecutive terms is the same r, right? So that's a common ratio. Whenever you have a common ratio, you have a geometric series. Okay, to show your work, show me the definition. The definition is actually defined as the sum of the partial sum sequence. To make the connection a little bit better, so can I write the meaning of the partial sum sequence in kind of this form? You look at here. The partial sum sequence Sn is defined as the sum of n plus 1 terms, I from 0 to n, and then you add r to the power of I, right? I from 0 to n, and then r to the power of I. The reason I'm writing in that form, I want you to see as n approaches infinity. You look at the mouse cursor. This number is going to be getting larger and larger positive, right? Larger and larger positive. it's kind of infinity. You try to compare these two guys, right? So you see that's how we use the sum of finitely many of terms to define the sum of the series in which there are infinitely many of terms. Okay. That's optional step. I included that so because it's easier to see what's going on. Yeah, probably that way. Okay. And then it's the same thing as the limit as n approaches infinity, the limit of the partial sum as n, right? We have computed as n. Now you just compute the limit as n approaches infinity. Okay, as n approaches infinity, we have a closed form in here. 1 minus r, and then 1 plus, 1 minus. On the numerator, you have 1 minus r to the power of n plus 1. Okay. Do you remember we have two cases? I told you more on y side last time, so this time you just need to show your work. Okay. As n approaches infinity, it means as n gets larger and larger positive. In this quotient, the only term which is dependent on n is that term. As n gets larger and larger positive, as n approaches infinity, this term approaches 0 for sure. I told you last time, right? Whenever, as long as the value of n is in between -1 and 1. I'm going to repeat. When r, probably I said something wrong. I'll try again. Okay. When r value is in between 1 and 1, when the common ratio is in between 1 and 1, the limit as n approaches infinity, the limit of that term is equal to 0, right? I told you y last time. So the whole thing will approach 1 over 1 minus r. The limit of that term is 0. So that term is dead. That term is gone, right? And then this is only true when r is in between -1 and 1. I hope it's not too squeezed. You write a comma here, you write a semicolon here, okay. And otherwise it's divergent. So I told you why last time. I showed you many other cases. It's diverges. You say the series diverges, or you say the series is divergent, right? You just write otherwise. By otherwise, I mean when r value is 1, it's divergent. When r value is -1, it's divergent. When r value is any number outside 1 and 1, like 2, like -2, it diverges, right? There are many other cases. This covers many other cases. Okay. Okay. Now we have an important conclusion for the geometric series. Probably I'm writing it too many times, but this one is too important. It's the basis of many convergence tests, which we may or may not have time to cover too much. But I want you to remember the important conclusions. Okay, the important conclusion. I mean, theorem. Okay. For the geometric series. So this time I'm going to officially introduce the term. We call the series geometric series. Geometric series. I starting from 0 to infinity. Again, the convention I'm making is still we treat the initial term 0. Okay. So, but not all instructors or all textbooks have that convention. It's only it's kind of my convention and probably some others convention too. Okay. The form of the geometric series is the following. Okay, r to the power of I. By that we mean initial term is 1, and then the next term is r. The term after that is r squared, and so on. Okay. You can omit all the arguments showing y. In the future, you can freely use the following. Okay. It converges to 1 over 1 minus r when if r is in between -1 and 1. We have seen that, right? And then you can say it diverges otherwise. Okay, I repeated the idea one more time, and then you are going to repeat the thing for the assignment one more time. So, okay. It's also useful if we see the formula the other way around. If we see the formula the other way around, we are trying to represent a function as a power series. Okay. So maybe I'm going to write again. So can I write two things? One thing is that actually the same thing. I'm trying to write the same thing twice. If you want to represent, now let's say a function of r, you just imagine 1 over 1 minus r is a function of r. The independent variable is r. Okay. You can represent that function 1 over 1 minus r as a power series. I mean, as at this time you just say geometric series. I did not say anything wrong. Okay, but very shortly I'm going to show you the meaning of power series. So probably I mentioned a little last time. Okay. So basically the function 1 over 1 minus r now can be represented as, can I just say power series? Okay. I starting from 0 to infinity, and r to the power of I, right? I forgot to mention the restriction. Actually, in here you have only one restriction. Okay, r is not equal to 1. When r is not equal to 1, the formula is true. Okay. Earlier we included. So how about we also include r value of 0? Okay. Still, I do not want to define 0 to the power of 0. Okay. Now look at the second item number 2. Okay. You imagine you have a function 1 over 1 minus r. This function can be represented by a power series as the power series I from 0 to infinity, r to the power of I. I say it power series, so because every term is a power function of r. Okay, you know what I mean. I mentioned last time. Okay, so very shortly I'm going to talk more about power series, but this is only true when r is in between -1 and 1. If you treat r as the independent variable, and then the representation is valid only when r is in between -1 and 1, in which I say -1, the open interval from -1 to 1 is the interval of convergence. It means the series converges only when r is in between -1 and 1. Okay. So today we are going to practice a few questions in that nature. Okay, how to use the formula. Actually, we are going to do quite a few questions using that formula. Okay. I haven't done part 1 yet. I haven't done part 3 question 1 yet. I will go over part 3 question 1 very quickly. I think I did 3 questions in one. In part 3 question 1. Now I'm going to do a few more questions using the formula. Okay. I will show the meaning. Now let me copy the questions to the PowerPoint first. I'll try to make the thing a little bigger so that you can see better. Okay, now question A. I told you the only formula you need to remember is that formula. Now we are trying to compute the sum of a series, and also determine the interval of convergence. It means for what values of x the series is convergent. Now you treat x as a variable. Okay. You see, so this time I will show you the difference. The difference between question 1 and question 2. In question 1, my intention was to ask you to use the limit of the partial sum, sequence to define the sum of the series. In question 2, I did not ask you to use the partial sum sequence. You just find two things. I'm just looking for the interval of convergence, and I'm also looking for the sum. Okay. The only thing we know at this time is the geometric series. So the only thing you can use is that. I'm going to go over questions one by one. Okay. Now let's do question A first. Actually, for this kind of question, the most important thing is to identify R. Okay. So that you can use the formula for the geometric series. For instance, for question A, if you do that on scratch paper. Okay. If you treat x minus 1 as R, so to be R, so that's scratch paper. That's not part of the solution. Okay. If you treat x minus 1 so to be R, so do you have exactly the form. So now let's say R to the power of I, and I from 0 to infinity. Again, I want to treat x minus 1 to be R, so you have the form of a geometric series. Okay. So that you can use the formula. So by that I mean the sum. Now we are trying to determine for what values of x the series is convergent. So we start by treating x minus 1 so to be R, and then we can see what's going on. Okay. So x minus 1, the whole thing to the power of I. Okay. If you treat x minus 1 so to be R, you can use the conclusion that the sum I from 0 to infinity R to the power of I is equal to, you can use that formula, right? It's equal to, I still want to represent the thing in two cases. It's equal to, keep in mind x minus 1 is R, right? So the sum is equal to 1 over 1 minus R. So this time you do not write 1 minus R. You keep R in mind. You write R is x minus 1. You write x minus 1 instead. Okay. So did I make the thing too complicated? Actually, the thing is easy. Okay, it's just the sum of R to the power of I. The sum of the series is 1 over 1 minus R. The conclusion we have seen before. But this formula is not true. It's not always true. It's true only when x minus 1 is in between -1 and 1. So that makes sense. Otherwise, it diverges. But in the question, when we are looking for the interval of convergence, we need for which values of x the series converges to that. Okay, so this thing I'm going to write in some better form, essentially the same thing, just in better form, so we can identify the interval of convergence. Okay, now the numerator is 1 over. Simplify the denominator. I think all of you guys can see it's 2. All of you guys can see it's 2 minus x, right? You have 2 minus x. And then you solve that inequality for x. I think I mentioned that last time a little bit, but the thing is when x minus 1 is in between -1 and 1, we want to solve the inequality for x. We want x is in between what two numbers. Okay. In order to do that, all you need is to add all the terms by 1. You add all the terms by 1. The inequality, the direction of the inequality is the same, right? You add all the terms by 1. -1 plus 1, you have 0. And then add 1 to the middle term, you have x. That's what we wanted, right? And then you add 1 to the right, to the term on the right, you have 2. By that I mean x minus 1 is in between -1 and 1. It's the same thing as x is in between 0 and 2. Right. So the given series converges to 1 over 2 minus x when x is in between 0 and 2. That's actually the interval of convergence. If you want to specify later on, I'm going to specify that. Okay. Still diverges otherwise. Diverges otherwise, right? Semicolon, comma, I mean the full stop there. That's how you write the math. Comma, comma, semicolon, full stop. Okay. We are also looking for the interval of convergence, right? So the interval of convergence is the open interval from 0 to 2. You just write the inequality form using the interval notation from 0 to 2. All right. That's how we do question 8. I'm going to jump to question C. Okay, so because this kind of question is not super important, probably I'm going to include a question like that on the assignment. Now you look at question C. Okay, you look at question C. Again, the key is how to identify R. And by the way, I'm going to make some comments on C. Okay. Now let's try to understand the series by looking at the first few terms. I'm trying to say when I value is 0, it will give you initial term 0. Okay. When I value is 0, you treat -1 to the power of 0 is equal to 1. Okay. And then initial term, and then x minus 2 to the power of I. I think the initial term is 3, right? And then the term after that is determined by I value of 1. I mean, the first term, I do not want to say the first term. I call that term 0. The next term is term 1. I'm trying to say term 1 determined by the index value of 1 is given by the following. Okay. If you compute, it's 3 minus 3 times x minus 2. Why do I have a negative sign in here? So because -1 to the power of 1 is equal to -1, right? That's how you have a negative sign. I think you have. I hope you can see the pattern now. But I believe the next term you are going to get is positive 3 times x minus 2 and then squared. Do you see how this -1 to the power of I functions? It shows you the terms are alternating. I mean the signs are alternating between positive, negative, right? I want to repeat this -1 to the power of I will, it means the series is an alternating series. It's actually an official name, alternating series. Okay. By that we mean the signs are alternating between negative, positive, negative, positive. It's handled by this -1 to the power of I. Okay. So later on you are going to see more. Of course, you have more terms. I'm going to write one more term, and then I will write dot dot dot. The term I just wrote is term 3, right? Term 0, term 1, term 2. I mean term 0, term 1, term 2, term 3. Okay. Term 3 is the fourth term. I hope it's not too confusing. Okay. Now I'm going to work on C. You guys are smart. So anybody want to tell me how to choose I? I mean how to choose R? As long as you can choose R properly, so that and then you can use the formula, the sum. So now let's say R to the power of I. You can use that formula. How do we choose R, or how do we think of R? Can I just say how we choose R? I from 0 to infinity. You have 3 here. If you combine negative sign and x minus 2, if you choose the whole thing and then to the power of I, that's valid. That series is the same thing as the given series. If you write the whole thing in that form, and then you can see how to treat it, what your R is, right? What's your R? The R is the whole thing in the square brackets. Can I say that way? Yeah, you got it. Okay, then you can treat the whole thing in the square brackets as R. So you have kind of the form R to the power of I, right? Now you can keep on going. When I do this question, I want to mention when computing that, it's permissible to take out a common factor. Actually, it's coming from. So you know the sum of the series is defined in terms of a limit of the partial sum. When computing the limit, you can take out the constant, right? The same thing. It's coming from that, but I'm not going to write the detailed proof. Again, it's permissible to leave a common factor out of the summation notation. I'm trying to say you can leave the constant 3 out of the summation notation. Again, the reason behind that is the sum of the series is defined in terms of the limit of the partial sum. I from 0 to infinity, and then you have the still use square brackets. You have x negative x minus 2, and then the whole thing to the power of I, right? Now you have R. R is the whole thing in the square brackets. Okay. Now we are ready to use the formula. So the given series so do not forget the constant factor of 3. You still have the 3 in here, okay? And then do not forget your R, okay? On the numerator you have 1, right? It's simple. On denominator you just have 1 minus R. You have 1 minus R. In this particular case, you have 1 minus your R is negative. Negative x minus 2, right? It's nothing but the sum I from 0 to infinity R to the power of I is equal to 1 over 1 minus R. So that's the formula. Okay. Of course, you need to give the interval of convergence. So this thing is true when negative x minus 2, when negative x minus 2, when your r is in between negative 1 and 1, right? It's probably two cases, and the diverges otherwise. Okay. I'm not going to rewrite many things, but I believe the function here is going to be, I don't know. Can I just, you could simplify the denominator, but the point I'm trying to say, okay, when negative x minus 2 is in between negative 1 and 1, I just want to talk about the interval of convergence. Okay, when negative x minus 2 is in between negative 1 and 1, this time I'm going to do it slowly again, but in the future I'm going to do it faster. Okay. When negative x minus 2 is in between negative 1 and 1, the first thing you want to solve the inequality for x. Okay, you want to get for when x is on what interval, the series is convergent, right? To achieve that, you solve for x minus 2 first. Okay. By that we mean you multiply all the terms by negative 1. So do not forget, when multiplying all the terms by negative 1, you change the direction of the inequalities. You multiply all the terms by negative 1, you change from less than to greater than. Okay. High school math, you learn that. Okay. It's not anything new. Negative 1 times 1, you have negative 1. Negative 1 times that negative 1. Can you see the mouse cursor? Negative 1 times that negative 1, you have 1, right? This is the same thing as x minus 2 is greater than, you look at here. You read from the right hand side. So you read from the right, so to the left. You have x minus 2 is greater than negative 1, less than 1, right? X minus 2 is greater than negative 1 and less than 1. Now you can use the same trick as we did for the earlier question. Okay. Now you add 2 to all the terms. You have x is in between. So this number 1 plus 2 is 3. Negative 1 plus 2 is 1. So I'm trying to say the interval of convergence. For this part, you can replace this part with the when x is in between negative. Sorry, I forgot already. 1 and 3, I think. And of course, it's possible to simplify the denominator. Okay, I'm not going to do that. You could write the whole thing as x plus or minus some number. It's probably x plus 1. I'm not sure, but it's possible to simplify that. But the most important thing is the interval of convergence. Interval of convergence is the open interval from 1 to 3. Do you have the denominator x minus 1? You have x you have positive x minus 2 and then plus 1. You have x minus 1. Probably you have x minus 1 here. I did nothing but simplify the denominator. In some better form, you could put 3 on the numerator. Okay. By that we mean the series converges to that function only when x is in between 1 and 3 on the open interval from 1 to 3. Okay. Okay, so we're done this question already. Okay. This question. Now the following questions are going to be designed to show you how to use the formulas the other way around. Okay, we'll do the first two questions first. Okay. After doing a few questions, I really do not have to go over too many questions on the list. Okay, I will go over a few questions. I'm looking for the definition of a power series. Okay, the definition is here. So can you see the screen? Okay, we say a series in that form, a power series above a. I will show the meaning. Okay, very shortly. By that we mean each term is a power function of x minus a. If that's the case, we have a power series above a. Or some people just say a power series centered at a. You're going to see why we call it a power series centered at a very shortly. Okay, you just try to remember the definition. When we do questions, I'll go back to compare. Okay, I will go back to make some more comments. Okay. Now let's work on question one. Question one is super easy. Okay, we just use the formula the other way around. Okay, the question, I did not copy the question. Okay, you look at the question. The question is asks you to represent each of the following functions as a power series above a. It's kind of the other way around. I give you a function. I want you to represent the function in terms of power series. If you can represent the function in terms of the power series, so later on we are going to use power functions to study many properties of the given function. We are going to see it very shortly. Probably you are going to see it today. It's because the power functions are the simplest to study in calculus. You know that, right? Yeah, in any case, we'll do question one first. Straightforward. You just treat x as r. Okay. Actually, for all the questions, the only formula you need to use is the following. To represent 1 over 1 minus r. Okay. The representation is so now let's say 1. Okay. I told you I really want you to get used to the summation notation. So starting from now, I always use the summation notation, unless I want you to see what's going on with this series. Okay, I from 0 to infinity, and then r to the power of I. You know that, right? It's always a good idea. Actually, it's kind of a requirement. Whenever you write that, you need to write the equation is valid when r is on what interval. Always write that. Okay. Whenever you represent a function, always specify the interval of convergence. So because for many other values of r, the equation is not true. Okay, the series is divergent. Okay, question one is simple. You just treat x as r. Okay, we have 1 over 1 minus x equals in terms of the power series. I from 0 to infinity. You just replace r with x. You have x to the power of I, right? That's how we represent that function in terms of a power series. This equation is valid when r is in between -1 and 1. Specify the interval of convergence, it means when x is in between -1 and 1, right? That can be treated as the final answer. If you write in that form, you have represented the function in terms of the power series, and you have specified the interval of convergence. Again, I want you to notice each term is a power function of x as x to some power. Okay. Each term is a power function of x. Why do we say centered at 0? You can write the power function of x as x minus 0 to some power. So these two things are the same, right? So it's a power function centered at 0. If you have a power function centered at 0, then I'm telling you now, why do we call it a power function centered at 0? Centered at 0 because the 0 is the center of the interval of convergence. So do you see this interval of convergence is from 91 to 1, and then the center of the interval is 0, of course, right? Okay, 你好, we'll move on to 2. Okay. Using the answer to question 1, it's easy to get the representation for 2. I told you it's permissible to multiply all the to multiply the series. It's permissible to put the factor into the series. Now let me try to show you what I mean. Okay, I will give you the answer in 2 steps. Okay, 1 over 1 minus x. In question 2, you have x, right? You have x, so which is the same thing as x times 1 over 1 minus x. Now, the second factor, 1 over 1 minus x, can be represented as a power series as the following. You have x times the power series. Now let's say x to the power of I from 0 to infinity, right? The next important thing I want you to know is it's permissible to multiply x into all the terms. After representing a function in terms of a power series, of course you need to specify the interval of convergence. This is valid when x is in between 91 and 1. Okay, and then we keep on going. Okay, we keep on going. I'm trying to say, according to the property I just told you, it's permissible to multiply x into all the terms in the power series. By that I mean, I will show you the answer, and then you're going to see what's going on. Okay, I from 0 to infinity, and then now each term will become x times x to the power of I. Now each term becomes x to the power of I plus 1. So that makes sense? I was trying to say on scratch paper only. Okay, x times x to the power of I is equal to x to the power of I plus 1. Okay. Again, whenever writing a series representation of anything, specify the interval of convergence. So this is true only when x is in between 91 and 1. Okay, so we're done question 2. So question 3 is kind of similar too. Okay, I will give the answer to question 3 so very quickly. Okay, the same idea, such as actually the main thing is how can you manipulate the function so you can see the form of 1 over 1 minus r, as long as you can see that form, as long as you can get your r, and then you have the representation using that formula. Okay. Anybody want to tell me a little trick so that you can see 1 over 1 minus r? What to do? You take out 2 from the denominator, or you take out 1/2 from the whole thing. Okay, I'm going to show you the whole thing. 1 over 2 minus 2 minus x. Okay, to represent the thing, I want to do something to make the denominator in the form of 1 minus r. in this case, it's just 1 minus x if you take out 1/2. So do you know what I mean? You can verify the equation now is valid. I mean, that equation is valid. Okay. Now you can apply the formula to that factor, to the box one. Okay. Apply the representation formula to that one. So you just have 1/2 and then the power series from 0 to infinity. Okay. And then you have x to the power of I believe, right? This thing is valid when x is in between -1 and 1. I think I'm going to keep on writing to multiply 1/2 in. That's not the final answer. You listen to me. That's not the final answer. So because the definition of power series, you have to write the series in that form. By that I mean every term you cannot have any number of functions before the series, and also any term has to be written as a number times a power function. I was trying to tell you why that's not the final answer. Okay, but it's easy to get the final answer, right? The final answer is going to be something like every term I want is a number times a power function. Now every term is 1/2 times the power function x to the power of I. If I distribute 1/2 into all the terms, you have this, right? I from 0 to infinity. You see, that's the final answer. All right, simple. Again, the key idea is to do something to make use of that formula. Actually, all the questions in this part are kind of in that nature. Until almost the end, I'm going to introduce some more properties. But okay, I think we can go over some more questions on that list. Can we skip question number 4 and just do number 5? Actually, my intention for question number 4 is to get you ready to do 5. But you guys are smart. We can go directly to do 5. Again, we want to use the formula. We want to make the function kind of in the form of 1 over 1 minus r, so that the only function now we know how to represent. So later on we are going to have way to represent many other functions, exponential functions, trig functions, any function, actually literally any function we have way to represent. But now at this point the only function we can represent is 1 over 1 minus r, right? How can we manipulate the function a little bit to make the function in that form? I will start from this. Okay, 1 plus x. So try to listen to me. So that's how you think. Later on, it's easy to deal with x. So you can leave out x. I mean, you can leave out the factor of x. Later on, you can always multiply all the terms by x, so that every term is still a power function above 0. So basically, why I do that? I want 1 at this location, right? That's the 1 at this location. Anybody want to tell me r? How do you write the denominator in the form of 1 minus something? Anybody want to tell me r again? Now the denominator is 1 plus x. How do we write the denominator in the form of 1 minus something? So please, I'm looking at the chat. exactly the main thing. As long as you can see that, then you know how to represent the function. I'm looking for something in brackets. So what should be in brackets, please? What's in brackets? It's negative x, right? Now, negative x is your r, right? Now, do you see the form? Here you have the form of 1 over 1 minus r. As long as you can see that, you can represent the function. Okay, x now, okay, and then you represent the form of 1 over 1 minus r as a series. I do not want to say a power series for now. Okay, as a series I from 0 to infinity. Okay, so here you have negative x to the power of I. Okay, it's kind of in the form we want, but not really. Why do I say not really? We want each term inside the series is written in terms of as a number times a function, a power function. I want to repeat, the final answer should be in the form that every term in the series is a number times a power function. That's what I meant. Okay. So did you see the trick? Before? Actually, I'm trying to use the trick the other way around. Again, after representing a function, I always want you to write the interval of convergence. Of course, in here you have negative x in between negative 1 and 1. So because when r is in between negative 1 and 1, the representation is valid. Okay. I'm trying to say that I will give you 2 more steps. Okay. I from 0 to infinity. Again, I do not want to treat that as the final answer. So because in the definition of power series, every term should be a number times a power function. So that's why I want to write the underlying term in terms of a number negative 1 to the power of I and then times x to the power of I. So that makes sense? Now every term is in the form of a number times a power function above x minus a. I mean a power function of x minus a. In this particular case, a value is 0. Of course, you do not have to write 0. Okay. Still, so this is true when x is in between negative 1 and 1. Okay. Finally, of course, in the form of power series, you cannot have a function before the summation notation. And by the way, so did I tell you the notation is the summation notation? Finally, the final answer is going to be something like negative 1 to the power of I from 0 to infinity. Okay, and every term will become x to the power of I plus 1 for the reason I told you before. Again, it's permissible to multiply x into all the terms in the series. That's the final answer. Okay. So because for almost all the questions are kind of the same idea, I'm going to jump to question 7. The same idea. Okay. So to use the formula for geometric series, we want to do something to change the function to the form of 1 over 1 minus r, right? So that's the only function we know how to represent. Of course, you're allowed to have something like x to some power, right? And stuff, or some constant. So the key idea is to to change the form of the function to what we want, to the form we want. Now the solution. The thing is, okay, can I just copy the thing again? The thing can be rewritten as you leave out x, right? and then on denominator you have 2 plus x. So this time you have two things to do. You have two things to do. You look at the mouse cursor. You want this location to be 1. You want the sun to be negative. Right. How about we do one thing at a time? We make this location, we make that location 1 first. Okay. To make that location 1, you take 2 out of the denominator, or you take 1/2 out of the whole thing. Now the whole thing, it becomes maybe 1/2 times x. You listen to how I think. The reason I do that is I want to make that location 1 the main thing, right? If you make that location 1, now the function now, so here it becomes x over 2, is that right? You have x over 2 at this location. I think you can check the equation is valid, but after that I created 1 at this location. And then to use the formula to represent 1 minus r in terms of a power series, we have to make this sign negative. I think we have seen the idea before, right? Now you have 1/2 x. Now this thing will become 1 minus negative x over x. X over 2, I want to repeat why we did everything. So because we want this location to be 1, we want the sun here to be negative, so that we can use that formula. So do you see? Now you see something in this form, a number times x to some power, and then times the form is 1 over 1 minus r. At this point, you see your r. Your r is the whole thing in the brackets. Now you're ready to use the formula. Okay. I will show you how to use the formula. So maybe I will squeeze something here first. Okay. I don't know if I have enough room, so that's why I'm writing the next step in here. Okay. You have 1/2 times x. Now the thing you do is to represent the series. To represent the function in terms of a series as I from 0 to infinity. Okay. And then r to the power of I. In this particular case, r to the power of I. Your r is negative x over 2, and then the whole thing to the power of I. Okay. We're close, but not done yet. Okay. Again, the final form should be nothing before the summation notation, and every term is in the form of a number times a power series. Okay. So this time we need to do a little bit more work. Okay. Of course, a good practice is after you represent a function, you write the interval of convergence. But we kind of keep on writing. So can I just write here? It doesn't matter. The representation is true when r is in between -1 and 1. I said r, but your r is negative half of x. Okay. Simple enough. We keep on going from here. Okay. Now we are trying to rewrite everything in terms of a number. We're going to rewrite all the term as a number times a power function. We handle the inside first. Okay. The inside series. I just copy 1/2 times x. I'm going to run a little bit slower. Okay. The inside the series, I'm trying to say I'm going to write all the terms as a number times a power function of x. Okay. You see the terms have alternating signs. So because you have negative to some power, negative something to even power, you have a positive sign. Negative something to some odd power, you have a negative. So did I say anything wrong? Negative something to even power, you have positive sign. Negative something to odd power, you have a negative sign. I think I said it right. every term, now I want to write every term inside as a number times a power function of x. Okay, so just try to follow me. In many cases, you leave out -1 to some power to indicate it handles the signs. Okay, you leave -1 to the power of I, and of course you need to leave out 1 over 2 to the power of I. Actually, I will tell you what's going on. Okay, so 91/2 to the power of I can be written as 91 to the power of I and then 1 over 2 to the power of I. Some simple high school math. Okay, and then you have x, so to the power of I. Okay, so do you see, if you represent the thing in that form, every term now is a number times a power function of x? You see that, right? Now one more step, and then we're done. Okay, so by that we mean in the last step you multiply 1/2 of x into all the terms in the power series. Finally you have the final answer, I from 0 to infinity, and then you still have 91 to the power of I. This will show you the signs of the terms are alternating. Okay, so the series is kind of alternating series, and then inside you are going to have 1 over 2 to the power of I plus 1. So do you see how you get I plus 1? If you distribute 1/2 into all the terms, every term is 1 over I plus 1, right? And still you have x to the power of I plus 1. For the same reason we have seen before. In the final step, I'm going to write the interval of convergence. I know in high school you were trained very little about the inequalities, so that's why I will still do that. Okay, multiply two sides of not two sides. Multiply all the terms by -2, I said. Okay, and then x is change signs. If you multiply an inequality by a negative number, you change the directions of all the inequalities. I meant to change directions. I think you have -2 here. I said you multiply all the terms by -2. Okay, so you have x in the middle. Okay. And on the left side, on the left, I mean, okay, on the left, I believe you have +2. Now you read from the right to the left, x is greater than -2 and less than 2. So the interval of convergence, the representation is valid when x is greater than the -2 and less than 2. Okay, that's the final answer. That's how we represent the function in 7. Okay, just leave the function in that form, the same thing, right? So we're done 7. Now you can see all the series, all the representations we did in the series, they're all centered at 0. Okay, by that we mean it's kind of okay. For this one, the interval of convergence is from -2 to 2. Okay, so the center of the interval of convergence is equal to 0. Or we can look at the representation. Every term is a power function of x. You treat x as x minus 0. So that's why it's a series centered at 0. Okay, power series centered at 0. Okay. I believe in next question I'm going to show you something not centered at 0. We'll do question 8. You're going to see, so this time the interval of convergence is going to be centered at 1. So do you see something like that already? So anyhow, we'll work on that question first. Okay. Still, you want to use the formula something like this: 1 over 1 minus r. But this time you want r to be x minus 1, so that I'm trying to say if you have the form of 1 over 1 minus x minus 1, and then later on the series, the representation of that is going to be the power series I from 0 to infinity, r to the power of I, right? X minus 1, the whole thing to the power of I. Now you see, this time you have a power series centered at 1. Later on, you're going to see the interval of convergence is going to be centered at 1. Okay. So, but anyway, anybody want to tell me how to manipulate the denominator so that you can? I told you already. I think I told you already. Okay. Just how to rewrite the denominator so that you can. Okay. It's in here. That's the solution. That is the solution to the question. So do you see it? Okay. The given function 1 over 2 minus x is equal to, again, how to represent a function is relevant to the value of a. If I want you to can you still hear me and see me? Hi guys, I saw some wrong message on Teams. Can anybody confirm you can still hear me and see me? And see the screen, I mean, so now see me.
Yeah.
Okay.
Yes, sir.
Sure, thank you. Okay. You do not need to see me, you just need to see the screen. Right. Okay, so now on denominator we have I told you the form. You convert the function to the form of 1 minus x minus 1. I told you why. So because we want to represent the function as a power series of x minus 1. Each term is a power function of x minus 1. Can I say that way? You look at the definition here. A value in that question is 1. So every term is a power series above of x minus 1, or we say it's a power series above 1, or a power series centered at 1, all the same thing. Okay. After you do that, you can so you see you have a minus sign, a required minus sign. You have x minus 1. So later on, I'm going to make more comments, but now let's complete the question first. Okay. So you have again, r is x minus 1, so it can be represented as a power series as x minus 1 to the power of I, right? I is from 0 to infinity. Specify the interval of convergence. Okay, so you have x minus 1 in between -1 and 1. The representation is valid when r is in between -1 and 1. Your r is x minus 1, of course, right? That's the answer to the question. So that's the final form. But a little bit of additional work you need to do is to get the interval of convergence. But this inequality is the same thing as when x is in between 0 and 2. You add all the terms. I mean, you add all the terms. You add all the 3 terms by 1. You add 1 to all the 3 terms. You want to make the middle x, right? -1 plus 1, you have 0. 1 plus 1, you have this 2, right? So the interval of convergence is the open interval from 0 to 2. Okay. So do you see the open interval from 0 to 2? So now, so 0 here, so 2 is here. So do you see the center is 1? Okay. The center of the interval of convergence is 1. So because in every term you have a value is 1, right? So that's why we call it a power series center at 1. Any questions about this? Simple, right? And now to contrast, if I for the same function, okay, also for the function in 8, 1 over 2 minus x, if I want you to represent the function as a power series above a value of 0, then the answer is going to be different. I will squeeze it here so that you can contrast the two cases. Okay, if you want a value to be 0, by that I mean I want in every term of the power series, I want every term to be a power function of x to some power. Then you would do something like this. I think we kind of see the question already. You leave out a factor of 1/2, and then the function becomes, can I write the equal sign from here? You have 1 on the numerator, you have 1 minus half of x in here, right? I think I got it right. And then in this case, your a value is half of x. So you have half of the sum from 0 to infinity. You have negative x over 2, the whole thing to the power of I. And then I will get you the final answer, okay? From 0 to infinity, right? You have negative 1, and then you have 1/2 to the power of I, and then x to the power of I. The final answer is going to be something like you multiply 1/2 in. The final answer you are going to have is negative 1 to the power of I, and then 1 over 2 to the power of I plus 1, and then x to the power of I. Of course, for this one, you also have to specify the interval of convergence. So can we do some more work here? The first step is true when x is in when negative half of x is in between negative 1 and 1, and that's the same thing as when x is in between negative 2 and 2. I think we have seen that before. So basically, for the same function, if I want you to represent the function as a power series above 1, the answer is different from representing the function as a power series above 0. I hope I made my point. That's for question 8. Okay. All right. Any questions? So which question I just did? We did 8, right? Okay, now we move on to question number 9. After question 9, I'm going to tell you some other properties. Okay. I think for question 9, I can go over the question a little quicker. I think you got the idea already. Okay. Again, I want to use the formula 1 over 1 minus r, right? That's the only formula I have. Still, that's the only function we know how to represent. So later on, after a little bit of new thing, we can represent some other functions. Okay. Yeah, that's why I'm going to convert the function to the form of I need a negative sign at this location. Okay. So you are going to have minus negative x squared. Right. You see your r is negative x squared. As long as you see that, then we are ready to represent the function as a power series. We are ready to do that. Okay. Again, r value, you treat r value to be negative x squared. So you have I from 0 to infinity. The function can be represented as the sum of infinity many terms, as your r is negative x squared, and then the whole thing to the power of I. Is that right? This thing is valid when negative x squared, your r is in between -1 and 1. Okay. Now all we need is to represent every term as a number times a power function of x. I from 0 to infinity. You have seen this many times, right? You leave out -1 to the power of I. It will take care of the signs alternative, negative, positive. I mean positive, negative, right? And then the whole thing remaining is x to the power of 2i. So do not tell me I plus 2. I was using the property x to the power of m, and then to the power of n is equal to x to the power of m times n. Okay, so don't be confused. This is valid when negative x squared is in between -1 and 1. Okay, when negative x squared is in between -1 and 1, you multiply all the terms by -1, right? It means x squared is greater than -1 and less than 1. Can you follow me? If you want me to add one more step, you would have x squared, positive x squared, greater than -1 and less than 1, so which is the same thing as that. But x squared is always non-negative. So do you know what I mean? X squared, something squared, can never be negative. So the given inequality is the same thing as that, right? This thing is equivalent to the absolute value. I don't know which way to tell you why. So there are too many ways. How about you just use your common sense. When a number squared is less than 1, the number has to be between -1 and 1. Okay. I'm trying to say the interval of convergence is still x is in between -1 and 1. Okay. So that's okay? You're good? Again, using your common sense, in order x squared is less than 1, the number has to be in between -1 and 1. We could do that by solving inequalities by using absolute values. I think common sense is okay. Use our common sense. Okay. So we're done question 9, right? Now every term is now in the form of a number times a power function of x now, right? So we're done the question. Okay, the next question is wonderful. Now you look at 10. So do you know what to do? Can you imagine what to do? The only thing we know how to represent now is 1 over 1 minus x. Now you have inverse 10. Okay, now the good news is it's permissible. I will show the property, okay? But you just try to remember, for a power series, actually for any series, it's permissible to differentiate term by term, and to integrate term by term, it's permissible to do that. More precisely, I will show you the conclusion. Okay, it's summary here. Okay. Now you look at this, the theorem. If a function can be represented using a power series centered at A, you know why it's centered at A, right? You imagine if you have a function that can be represented using a power series centered at A. Now, to differentiate the function, all we need is to differentiate all the terms, and then you add up all the terms, you have the derivative of the function. So do you see for this one, I could highlight. Now the highlighted is actually the derivative of that term. The derivative of the power function is equal to that, right? Probably you have to use a chain rule, but it's simple to see that. Or you just remember, if a function can be represented as a power series, and then it's permissible to differentiate term by term in order to differentiate the function. Okay. So likewise, it's permissible to integrate the function. It's permissible to integrate term by term. Indefinite integral, of course, you have a c involved, right? The arbitrary constant c. And then you look at the inside. Every term is actually an antiderivative of the terms in the series of the given function. So maybe I did not say it clear. You look at here. Every term in the series, in the power series now, is the integral is an antiderivative of the corresponding terms in the power series representation of the given function. Now I said it right, I think. You just remember it's permissible to integrate term by term. Okay, so that's the main thing. Okay. In addition to that, I forgot to mention something. Okay, the radius of convergence is going to be the same, but the interval may not be the same. Probably I haven't told you the meaning of the radius of convergence. Okay, but so can I just say the radius is actually half of the length of the interval? Now let's say in this case the radius of convergence is 1. It's kind of the interval from -1 to 1. You treat that as the center at 0, right? You have r in here, you have r in here, you have negative r in here. Okay, you just imagine center at 0. You use a compass to draw a circle. Okay, with the radius of r, so you have the interval. Okay, or you just imagine it's half of the length of the interval of convergence is the radius. The conclusion I'm trying to tell you here is the interval of convergence is the same. Sorry, the radius of convergence is the same. The only difference is one of the two endpoints. Okay, by that I mean after integrating 1 or -1 could be in the interval of convergence. I will show you the meaning very shortly. Okay, but now let's work on the question first. Okay. How about I will start over, okay, to show you how to do a question like that. Now the solution. Okay. The first thing you do is to differentiate the function. You do not know how to represent that, but you know how to represent the derivative of the function, right? After getting the representation for the derivative, and then you integrate back. So that's the idea. So the first thing you do is to differentiate the function, the derivative of inverse tan of x. All of you guys know that, okay? The derivative of inverse tan of x is equal to 1 over 1 plus x squared, right? You know that. Now from 9, you have to repeat the procedure. From 9, you want to represent the derivative of inverse tan. So by that we mean you represent, let's say, 1 over 1 plus x squared using question number 9. Using question number 9, I'm trying to borrow the answer to question 9. Okay. In question 9, we have represented the function in that form, right? This is true, I believe, when x is in between -1 and 1. Right. Now, how can we go back to inverse tan of x? We integrate two sides of the equation, right? We integrate two sides of the equation. We integrate two sides of the equation. For the left hand side, you have now you have inverse tan of x. Maybe I'm going to write one more sentence to show you what's going on. Integrate the equation, the above equation, okay? Integrate the equation. We have on the left you have the antiderivative of inverse tan of x. So recall what we did when solving separable, so differential equations. The same thing. Okay, you integrate two sides of the equation. On one side you have antiderivative, right? On the other side you do something, and then plus c. So can I write c in here, and then plus. So this time it's permissible to integrate the sum. It's permissible to integrate term by term. Now all we need is to get antiderivatives of all the terms. Okay. You watch me carefully. You still have the constant -1 to the power of I. Okay, and integrate the function. It's, you know how to get antiderivative of the circle, right? Antiderivative of the circle, you have x to the power of 2i plus 1, right? And then on denominator you have 2i plus 1. You know, antiderivative of a power function, you just imagine 2i as n, right? X to the power of n plus 1 over n plus 1. The same thing. And of course the thing is valid when I is from 0 to infinity. Okay. Now the equation is valid. So do you remember the radius of convergence is not changed? Is not changed. At this point, I want to write the radius of convergence equals 1. So because for this one the radius is 1, right? Radius is half of the length of the interval of convergence. So the radius is 1. Very shortly, I will tell you the difference why I say the radius is 1. But now there's a constant c involved. Using the trick we did before, a particular value of the function will determine the value of c. Okay, Now, the next thing we do is to determine the constant c. Why many people suddenly left class? It's okay, so there could be a connection problem, but I'm recording the video. It doesn't matter, okay? Now we are going to use a particular value of x to determine the constant c. Anybody want to tell me what value you want to use? We want to use x value of 0. We're going to do that, okay? We let x value be 0, and then the left hand side is going to be 0. Inverse time of 0 is equal to 0. And then the right hand side is equal to c plus. For the right hand side, you replace all the x's with the value of 0. So do you see if x value is 0, then all the terms are zeros, and then the sum of all many zeros is 0, of course, right? So I mean the series part is equal to 0. So we have c value of 0. Okay. Finally, we have the representation of inverse tan. So inverse tan of x now can be represented in terms of the power series as I starting from 0 to infinity. Now the form is that, I hope it's not too messy in here. Can I write this so? I think you can follow. Okay. C value is 0, so the representation of inverse tan of x is -1 to the power of I, right? And then on numerator you have x to the power of 2i plus 1. On denominator you have 2i plus 1. Now I'm going to give you the interval of convergence without proving. If you want to know why, if you have time, so probably we do not have too much time. I will give you the interval of convergence without telling you why. Okay. Now the interval of convergence is 1 and a -1 are included in the interval of convergence. So do you see, for this one, the radius is still 1. The given one, the given representation, I mean the representation of 1 over 1 plus x squared, the radius is 1. The interval is from -1 to 1, without including the two endpoints. But for the representation of inverse tan, the two endpoints are included. They still have the same radius of convergence, but the interval, they differ by a little. Okay. Again, I take that for granted now. I haven't told you why. If we have time, if you can give me one extra class, I can tell you why. Okay. We could talk about some convergence test, but so because of the technology problem, we lost one extra class. I'm not sure. I might talk about that in case we have time. Okay, so that's the complete solution to question 10. Okay, so that's how we represent inverse tan of x. To summarize a little bit, I'm going to summarize a little bit. Okay, now listen to me carefully. Okay. To represent inverse tan, the only tool we have is to represent 1 over 1 minus x. Okay, you have to differentiate the function, and then you try to represent the derivative of the function, and then you kind of integrate back. So you have the representation of the given function. After integrating, in many cases, there's a constant c involved. Okay. And then to determine the constant c, what I'm trying to say, to determine the constant c, you use a particular value of x. We have seen the idea already. Okay.